about we want 2 sigs in the answer, but let me ask you, pressure's going up. What do we expect to happen to volume? Go down. So, this is problematic for my students. I've seen it for years now. If the unknown is on the right-hand side, because in math, your big X, your unknown is always on the left-hand side. If this is problematic for you, take this thing and move the whole thing around. But you're going to have this times this divided by 2.4, and it's going to be so many liters. Allison, what did you get to the correct number of sig figs? 6.0 liters. Okay, is that what other folks got? Okay, great. Everybody's kind of comfortable with boil. Okay, let's go on. Let's take a look at the next law. The next law is Charles' law. Now, what I find really interesting about Charles' law, first he's French, and he did his work in the 1800s. And that to me is so interesting. Here Boyle is working in the 1600s and comes up with the first gas law. Almost 200 years later, Charles starts doing experiments, changing temperatures to see what happens. That would never happen today. See, back then, the only way they could communicate is write it out in a letter, okay, and have somebody pay a messenger to take it to scientists in another country. And it did happen. They did it all the time. But it was slow. Of course, it didn't take 200 years to deliver a letter. But just science was moving very, very slowly. If today, let's say we knew nothing about gas behavior, but today somebody does what Boyle did, that would be on the internet immediately, and there would be people at other schools say, aha, if he changed the pressure, I'm going to change the temperature, and within 24 hours those experiments would have been done. So the rate of increase in our knowledge is exponential. Also, this is what I really like. Why was Charles interested in gases? He was a hot air balloonist. Now, if you're sitting in a basket under this big balloon, several hundred feet in the air, wouldn't you be real concerned about the volume of that balloon? And so that's what got him started doing the work. Now, he was not the first hot air balloonist because they did it years before. When they had their first hot air balloon with the basket, they were so afraid that it wouldn't work, they didn't put people in it, they put animals. And I think they used, oddly enough, I think it was a sheep and a goat and a goose. Now, is that one weird combo to put? Anyway, that was the first thing that went up over Paris. And people went out to watch the animals going through the air there. So, let's take a look at this law. So here's Charles' contribution. He held N constant, how much gas he had, and he held pressure constant. And so what he was interested in is the relationship with the volume and the temperature. And what he found from his experiments, and you don't have to write all this down because I'm going to do a derivation like I did before. He found that the volume is directly proportional to temperature if it's in Kelvin. Because see, we've got to avoid 0 and we've got to avoid negative numbers for this to be true. I had the opportunity on New Year's Day 2008, I rode in a hot air balloon across the Serengeti in Tanzania to be up there watching the animals down below on the Serengeti plain. We were up there when the sun came up, and they had like 16 people in the basket, and we were in this tiny little thing. The guy running it, I thought it would be really quiet, because when you see it in movies and on TV, it's so quiet with those balloons going over. It was incredibly noisy because he's got this torch, you know, that he's heating up the gas to get it to expand if you want to go up, and he cuts out his torch. It's gas powered to go down, and he told us you can't direct the thing except going up and down. That's the only way you can direct it. So you've got to know a whole bunch about wind currents, because if you don't want to land here in the middle of the predators, I had visions of going down in a pride of lions or hyenas or whatever. So the way he had to do it, he had a GPS system that he could tell where the air currents. So if you wanted to go this way, you went up to where the wind was going that way. And if you want to go that way, you hunted for where the air is going the opposite way. And you hoped you could land where you wanted to. So we had spotters on the ground in trucks following us, just in case we landed in the wrong place. We could outrun a lion. So I probably was the only person in that basket that was thinking, Charles' Law. Okay, so V is proportional to T. Well, again, same old story. Chemists hate proportionalities. And so we like to turn it into a nice equation. So we put in a proportionality constant. Not the same number as before, just a constant, some other constant. Okay, let me rearrange. I'm going to divide both sides through by t because I want my variables on one side, I want my constant on the other side. So I'll divide both sides through by t, which makes it cancel here. So the ratio, V over t is equal to k. Okay, same story as you heard before. You go in first thing in the morning, you measure the volume, you measure the temperature in Kelvin. Then you come back and you repeat it. It's still equal to the constant, so the ratio is going to be a constant. So same story. If k is equal to k, then this must be equal to that. So Charles' Law is going to be V1 over T1 is equal to V2 over T2. Now let's take a problem. And this is 12-3. I'm skipping over 12-2. That's one you can look at, or we'll start next time reviewing by doing 12-2. This time, it says we have a sample of nitrogen. But you know what? It doesn't matter. Because any gas we took, we could do this same stuff with. So last problem, it just said some gas. This, it says nitrogen. So we have 117 mils at 100 degrees Celsius. At what temperature in Celsius would it occupy 234 mils? And then here, I put in a hint. Assume N and P are constant. So we look at that, and that is a classic Charles' Law. V1, T1 is equal to V2, T2. And again, we have 4 variables. In the problem, they got to give you 3. Okay, let's make a list. V1, Bruce, is 117 milliliters. Okay, T1 is what, Andrew? 100 degrees Celsius, but I want you to get into the habit in this chapter. Don't even lift your pencil. Just say plus 273. Number 1 mistake made in this chapter. You forget you need Kelvin. And the dirtiest trick that the test bank can do is if they say 273 Celsius, it looks good to you. Do you see that trick? No, you still need to add 273. And so we have 373 Kelvin. So just get in that habit. Now, what else do we know? We know V2. And Meredith, what is that?
234 milliliters.
234 mils. Now, before you start punching the numbers, there's 2 or 3 things to think about. When we end up, how many sigs do we want in our final answer? 3. Okay, now, check out for consistency. Since you have V on both sides, they've got to be the same units. We got mils, we got mils. No problem. And when we solve for this thing, we're going to get Kelvin, but notice it's going to ask us Celsius. Okay, so there's hurdle 2 in this problem. They give you Celsius, They ask you for Celsius, we can't work it in Celsius. You go Celsius to Kelvin, get Kelvin, switch it back into Celsius. Can you see if we worked a problem where it says 0 degrees Celsius, this would be worthless because division by 0 is undefined. So that's why we had to go to the Kelvin scale to avoid 0 and to avoid negative numbers. Okay, let's stick them in and see what we get. We got 117 over 373. And then we've got 234 over T2. And first, I want to hear what this is in Kelvin. And then we'll worry about Celsius. So do you have it punched, Bruce?
746.
746 Kelvin. And then, Andrew, what do I need to say? I want to switch it into Celsius.
473.
473. And how did you do that?
Just minus 273.
Yeah, just subtract. See, there's an item 1 up there, need to know. Get into Celsius. Now, is this realistic? Volume went up. What do you expect temperature has to do? Go up. Remember, it's a direct proportion. So, yeah, we expect temperature to go up. We started at 373. We ended at 473. Do a reality check. Is volume goes up, what happens to pressure? Goes down. As volume goes up, what has to happen to temperature? Goes up. That's assuming the other variables are held constant. Okay, now, let's take a little side trip here. We got to talk about STP. And it is not a gasoline additive. STP for us stands for standard temperature and pressure. STP, standard temperature and pressure. Okay, now, why do we have to define standard temperature and pressure? Here's why. Let's say my Monday, Wednesday, Friday class are running an experiment, and they're running a reaction to generate some gas, like the chemistry in a bag, and you work with the kids over there. Okay, and their grade is going to be dependent upon the volume of gas they get. Okay, the day they're working in the lab, the air conditioner has broken. It's really hot in the lab. Normal atmospheric pressure, but it's really hot in the lab. They get this gigantic volume. Okay, you go in to do it. You're Tuesday, Thursday. You go in, the air conditioner's fixed. In fact, it's fixed too well, and it's really pretty cold. So you go in, same atmospheric pressure, but it's really cold, and you get this little tiny volume. Should I give them better grades? Not necessarily, because for us to compare a volume of gas from Monday, Wednesday, Friday to volume of gas for my Tuesday, Thursday, you've got to compare it under the same conditions. And so what people did, they defined standard. And they made, in my opinion, a really stupid decision. Standard temperature that they chose, 0 degrees Celsius. Now, that may be an easy number to remember, but it's dumb. Because 0 Celsius is 32 Fahrenheit. Is anybody going to be working in a lab that's at 32 Fahrenheit? I would hope not. That our water would be freezing. Our pipes would be freezing. We would be freezing. So you never work at 0 degrees Fahrenheit. Or 0 degrees Celsius or 32 Fahrenheit. So they chose a number that made us all do a bunch of calculations every time we generate some gas to be measured. So that's their standard, or this would be what in Kelvin? 273. 273 Kelvin. Later, you know, this first work was done in the 1600s on gases, and this is what they chose. Later, when areas of chemistry called thermochemistry and electrochemistry came along and the chemical engineers got in on the act, they redefined standard. And they said, let's make it 25 Celsius. And that's about room temperature. A much smarter decision. But when we're here in the gas law chapter, take it as 0. Now pressure, they were smarter, at least for us living at sea level. They chose 1 atmosphere, and what would that be in torr?
760.
760 torr. Now, why I say that's nice for us, because an ordinary day here at sea level is 760. But if you worked in Denver, Colorado, they advertise themselves as the Mile High City. An average day in Denver is 630 torr, which means if they're doing gas law stuff there, they're recalculating not just for temperature, but they've got to recalculate for pressure as well. So standard temperature and pressure, need to know. Put that on your list. STP, 0 degrees Celsius or 273. And pressure is 1 atmosphere or 760 torr. Need to know. Now let's get to the most important section that you've heard today. And that's section 12-7. And in 12-7, they talk about the combined gas law. Okay, what they did here is they took Boyle's law and Charles' law and put it together. So you don't have to memorize 2 separate laws. And this is how it came out. P1, V1, P1 is over T1 is equal to V2, P2 over T2. Okay, and that is a need to know. I think that number 4. Now look at this. Let's say temperature is constant. Well, T1 and T2 would cancel. And there you sit with Boyle's law. Okay, on the other hand, let's say pressure is constant. So P1 is equal to P2, they cancel. So out they go, and there you have Charles' law. So here's both laws. There's absolutely no reason to memorize those 2 separate. Put it together. You can always use this if you have changing conditions. And that's a super important idea. And I'm going to put it right down here. If changing conditions. If they say, we have this gas sample, and you don't even have to know what the gas sample is, because this is true whatever gas we're working with. If it behaves ideally, and we're going to assume our gases will act ideally. This is the equation that you use. If it says anything, you start with these conditions and we're changing to these conditions. Or they'll say, we start at these conditions, what would the volume be at STP? And that is a very typical classical problem. We're going to have another equation. We may have it today, but it may be Tuesday before we get to it. The second major equation. And this is called the ideal gas law. It is used in a different way, and we may or may not get to use it today. But it's just, here is a sample of gas. There are no changing conditions. So that's the thing to look for. No changing conditions. So pressure, volume, N the number of moles. R is a proportionality constant. Instead of using K when they combined all the laws, they called it R instead. It's just a constant times temperature in Kelvin. What this one is used for, and this is probably the biggest mistake that people make in this chapter. You have this hugely important equation, and we have this hugely important equation. But when do you use which? Okay, if in the problem you see changing conditions, this is the one to use. On the other hand, if you have a gas, but you know some of the properties, but there's one that for some reason you cannot measure. Let's say you've been able to measure the volume of your gas and how many moles you have and what the temperature is, but your pressure valve, the gauge, just broke. So how could you get the pressure? There's going to be one missing part, and so you use PV is equal to nRT. One of my students years ago came up with this. She referred to this as the pervert equation, and with a little imagination, pervert. Here, so the pervert equation for no changing conditions. Okay, but